right, we're very happy to have Qiuyu to tell us about the Khovanov skein lasagna module of smooth fourfold, part one.
Four manifolds. Okay, great. Thanks very much for the invitation to speak here. I'm a non-dimensional topologist, and more precisely, I'm interested in studying smooth four manifolds. And very recently, a few years ago, there is this package of smooth four manifold invariants called skein lasagna modules that was constructed by Maurice and Walker and Gaugy. Today's will be a sequence of two talks. And today, I just want to give a quick introduction to the construction of skein lasagna modules and some formal properties enjoyed by this invariant, etc. So to get started, I want to talk about what is a link homology theory. So if you don't know the skein lasagna modules yet, this is you can think of it as a package of upgrading a link homology theory to four manifold invariants. And I will make that precise, but let's first talk about link homology theory. So I will be restricting to link homology theory in the three sphere. Link homology theory has three. It's nothing but a functor. I'm not going to state this in a more general way, but let's just say this functor is called.
Can I just ask a question before we go on to homologies and stuff?
Yeah.
Just as to the nature of the variant you will get, could we get a three-dimensional analog of this? So, for example, transformers and quantum groups give you invariants of knots and three dimensions. Right? Here, and so you get, and if I don't have knots, I get an invariant of three manifolds. Right? Am I going to get here an invariant that's like that I've also got invariants of simply four manifolds, period? Or I'm more like getting an invariant of knots and three manifolds that actually doesn't know about a three manifold without a knot. In other words, if I forget about knots, I get just a trivial invariant.
You can get an invariant for three manifold out of this package, but it will not be an invariant for knots in three manifold. It will just be invariants for three manifold itself. And I think of this invariant as maybe one level more categorified than most TQFT we know so far, like cyber-readers, figure 4 or other invariants, in the sense that it is going to assign to smooth four manifolds vector spaces rather than numbers. So to three manifold, you will get categories, vector spaces. Okay, great. But how to start our input will be a link homology theory. A link homology theory, to me, is just a functor to the comparison category of links in S3. So let's say, for simplicity, the category of vector spaces. So vector is a category of vector spaces over a field of your choice, and linear maps between them. And links S3 is the comparison category of links. In S3, then it has objects given by links in S3. A link, if you don't know non-dimensional topology that much, is just a disjoint union of circles embedded in S3. And I guess you can decide what adjective to add here, but usually one can add orientations or oriented links and some normal framing, frame links. So let's say oriented and framed link here. That is to say, if you move this surface sigma in the interior a little bit, deform it somehow, that is not going to change the class it represents in the morphism space.
So the hom is like a set?
Yes, yes. Or maybe I should write morphism. Okay. So in particular, so here, but my objects are concrete. This is somehow important. And well, isotopic things may not give you the same image under the linear conversion theory. But from the setup, it will be well more or less clear that somehow isotoping on my things is not going to change the output homology. So to make that precise, let's say if I have a big isotopy indexed by time parameter from 0 to 1, this is a big isotopy. Isotopy from L0 to L1 inside S3. Then from considering its trace, by its trace, I mean you take T at the first coordinate and LT at the second coordinate. Well, I guess the union of those from 0, 1. This is a conversion from L0 to L1. Therefore, it induces a map from the homology of L0 to the homology of L1. And this is actually an isomorphism. Why is that? This is because if you run this isotopy backward, LT stacks with its reverse, then the L1 minus T from 0, 1. This gives the identity conversion up to isotope. As you can check by some method. So really we could speak about, for example, the homology associated to a trifold without worrying about what exact trifold and choosing exact sphere.
So when you say vector, you mean graded vector space?
Yeah, you can put also some adjectives, grading, filtrations, etc. Yes.
Do you require that the surface will be connected in some sense?
No, I'm not going to. So my links in general will not be connected.
Okay.
And in order for identity morphism to exist here, identity morphism is going to be my link times an interval 0, 1. That is not going to be connected. So
So I mean that you allow that to be cut in the
Yes.
middle of the surface.
Yes.
sorry. So the entire boundary of my surface should only be contained in the bottom and on the top.
Like I'm can shrink to nothing.
You will cut from middle to axis.
Oh,
Upper half and lower half.
like this.
You can cap
needs slightly more conditions than just a function like this to build out the skein lasagna modules. And I'll next going to explain the actual conditions that allow us to build the skein lasagna modules. So below we will assume, in addition, that two additional properties. First one is you can consider the pi1 SO3, which is equal to Z2 action on say Z of L is trivial for L lies in S3. What does this mean? Well, SO3 acts on the 3 sphere by rotation. Well, maybe more concretely, a generator of pi1 of SO3 is given by rotation by some theta, going from S3 to S3, rotation by theta along some axis. Then pi1 is generated by rotation from when theta goes from 0 to 2 pi.
So it's like I can restrict to R3, it's the usual location.
Yes. Yeah, you can think of the rotation along the z-axis in R3 and then extend to the infinity by n. Then this ice, then rotation theta of L, theta from 0 to 2 pi gives an isotropy from L to itself just by rotating it 360 degrees. This induces the identity map ZL to ZL. And the second actual condition we want to impose is that Z is monoidal in an appropriate sense. If I take the disjoint union of two links, L1 and L2, this is going to be canonically isomorphic to the tensor product of ZL1 and ZL2.
map to the same thing, but it doesn't mean that, like, the invariance will be trivial, but it doesn't mean that the coordinates will be not trivial, and it may not actually matter. In other words, I could have done the same multiplication for Khovanov homology and gone, you get a different variance from the reduced invariance, but so what? But okay, go ahead.
Okay, great. So maybe people got young and going to give some examples you can keep in mind of such incohomology theory. The first one is rather boring. It's called, well, it got a fancy name if you like. It's called Khovanov-Rosansky Qiuyu Ren homology. So well, more generally, I guess Khovanov and Rosansky define the Qiuyu Ren homology for any for any positive integer n. But in the case when n equals to 1, this is actually a very boring theory, as you will see. So this is a functor I'm just going to denote by h from the horizon category of things, the category of vector spaces. And well, it sends any link to the one-dimensional vector space F, your base field. And it sends every horizon sigma, which is a map from h L0 to h L1 to sigma L0 to L1. This is, well, this is simply the identity map. Sorry, I'm so used to rational computations on this one-dimensional vector space. So this is not giving anything. It's a very boring variable. But as a test case later, we will also use this as a very first input to the skein lasagna modules and see what we get from here. Okay. All right. Next example, I will not explain this here, but maybe if I have more time, I will talk about this.
It's a little funny, right? I mean, if I, in Qiuyu theory, if I study Qiuyu invariance of GL1, it's not quite true. I mean, yeah, there's some grading, so it's not true that.
That's right. Right. So in general, this will be by grading.
Yeah, then the grading is not that boring.
Yes, the grading records more or less the framing of my the rise of my framing. So everything will be framed, I guess, if you want the gradings to be precise. Then you get some framing information for it, which are encoded here. But that's more or less the only interesting information. But let's forget. Let me forget about framing or gradings for a moment to make this simple. The second example is well, Khovanov-Rosansky GL2 homology. Or this is also known as just Khovanov homology. It is Khovanov's original construction of a categorification of the Jones plane volume. This, maybe I'll write KHR2 as a functor. You can also put a backgrading here, but I'm going to omit that in this first introduction. I think in the next talk, maybe I'll talk more about this Khovanov homology version of skein lasagna modules. But in this first talk, I want to make things general. So just to give you some feeling, the Khovanov homology of the trifoil dot And after the band attachment, I have yes, I have listening here, which is the home. So having that understood, I can talk about what is the induced map given by this cobordism. This cobordism, well, in terms of some basis, which I haven't told you, this is going to be just a matrix 1, 1, 1, 0. I guess I'm not saying much more than this having rank 3. But,
Sorry? That cobordism, it looks like a saddle.
yeah, this is a saddle cobordism. We are not going to be using this again in this first lecture. Okay, now let's move to the second part, which is skein lasagna modules. Again, this construction was due to Morrison, Walker, and Logic. In 2019, I think the published version is 22. So the invariant will be associated to a pair of first smooth compact oriented full manifold. And then second thing is a link. Let's say oriented. Yeah, I think I will always want oriented here, according to your mood, you may want to add more adjectives like furlings, etc. Link. On the boundary of the manifold X. So X may have boundary, it may be closed. When it's closed, I just take the boundary link to be the empty link. And then the skein lasagna module will be associated to this pair. I guess with input module C, this is the let's say just the vector space given by the following formula. So the location is script S sub 0 after Z X L. This is going to be spanned by so maybe let me write this down first and then explain. It's going to be spanned by pairs of a surface which is called a skein, and a label V which is called a decoration. And the whole pair is, you can just call it a decorated skein or
sigma is a smooth surface. Do you allow this to be like web or foam?
Not here. You can do different versions as you like, but I'm going to present the most primitive version.
Okay, but those versions do exist.
Yes. Okay. How about that? So I have my full manifold, I have a link on its boundary. My skein will be some surface in the interior, but outside a finite number of pores. And the boundary of the skein will be, well, on the boundary of my full manifold, it will exactly match this input, this boundary in L we have. But on the boundary of those input balls, you can also get some boundary components. So this is L. Here I may get some other component of my boundary, L1, L2, L3. Boundary sigma restricting to boundary X being L. Boundary sigma restrict to boundary BI given by some LI. And finally V is a label in the homology. Let me say the tensor product of the homologies of LIs. And I will be referring to those BIs as input balls, and those LIs as input links of this lasagna field.
So what does the subscript 0 mean?
Yeah, that's a great question. I guess in general you can, there's something called block homology, which was degree 0 gives this. But you might need some different assumption in the input link homology. But those are more, I have no idea how to calculate DR degree 0. But this 0 notation somehow starts here.
So this is like a cobordism from the disjoint balls. As disjoint S3s into this final picture.
Yeah, you can think of it like that. Yes. So we are not finished here. So we are taking the linear combination of a giant space, but to make it more reasonable, we will need to model out some skein relations. Just if you are familiar with the three-dimensional skein module, we also take the linear span of all links, but we model the Kaufman bracket skein relation, for example, to make the result manageable. Otherwise, you are just taking things without any structure. We shouldn't expect you to get any meaningful value. And now I'll explain what are those skein relations.
You're taking the direct sum over all possible number of balls and all possible links
Yes.
inside.
Yeah, that's right. Yes. So this K is not fixed. It can be anything, any finite number. dragging some of those balls along while I isotope, this is not going to change the class it represents in the skein lasagna module. The second relation is linearity in the label, in the decoration. Which means that if I have a lasagna filling sigma V, and I have another lasagna filling with the same skein sigma, but with probably another label V prime, then I can add them up in a linear way in my labels. This is just something we should do. And finally, there is a more interesting piece of skein relation, which I call the enclosement relation, which is the following. So again, I'll try to draw a picture. So suppose in a local part of your lasagna filling over there, you see some local picture containing a number of input balls and some parts of your skeins, maybe like this. And also you have your labels. So by the way, here I said the decoration V is an element living inside the tensor product of all the homology of the input links Li, but since we declare the whole thing to be linear in the labels, I can as well only allow V to be a pure tensor, namely V1 tensor, V2 tensor, V3, etc., one for each input link. So if V is a pure tensor, we can alternatively, I guess, put the decorations on each of the input ball, boundary of the input ball. So I put a VI here, VJ there. The relation is the following. So suppose you can find a slightly larger ball, say this one, although B prime, that encloses some parts of your lasagna filling. Then you can declare that the original lasagna filling is equivalent to the one obtained by deleting everything inside this larger ball, keeping everything else as it is. And update the label accordingly. So originally I have labels VI, VJ, but I need to update that to a new label V prime on my new boundary. But that is done by so I'll write a formula, but I'm going to explain this more carefully. So V prime is the image of VI tensor VJ under the conversion given by the part of the skein inside B prime. So if you look at sigma intersect B prime. If you look at sigma in the part inside going from Li disjoint Lj to this new link L prime.
Sorry, but the Li is leading in S3, is from union S3.
Yes. That's the part I need to explain. Very good. So it's a conversion from Li disjoint union Lj to L prime, but as Paul pointed out, Li and Lj are leading in different S3. So before making sense of this, we really want this to be a convergence in S3 times an interval. But currently it's not. So the procedure, the precise procedure for defining that is that I first choose some path connecting up all my input balls, in this case Bi to Bj, and then I indeed a terminal neighborhood of this path. Therefore, connecting all my balls into one single ball, and then do this evaluation. But by general position, this path I choose will be my surface. So you do get a comparison from Li disjoint union Lj to L prime.
How does the map depend on path choice?
Yeah, that's another great question, and I think I don't have time to explain, but the independence of the choice of that path is coming from those actual conditions. I guess most people know. Okay, and that's all. That's the whole definition. But I should maybe emphasize that here the input balls Bi are not; those are not concretely parameterized. In other words, the concrete diffeomorphism between Bi and a four ball is not specified. Therefore, before talking about the homology of Li inside such an unparameterized S3, you need to do some extra stuff. But the parameterization issue again is resolved by this number one. This number one, if you like, SO3 is homotopy equivalent to the mapping to the diffeomorphism group of the free sphere. This is by the so-called Snell conjecture, proved by Hatcher. And once you realize this, some actual work tells you that to get rid of all parameterization issue, you just need to kill this one non-trivial action.
Sorry. Is it right that technically a lasagna filling should not just be the skein and the decoration, but the skein and the decoration and the input balls and the input links?
Yeah, that's right.
Okay.
Yes. Okay. And I guess as a piece of notation, I will say the skein lasagna module of my format of X without the boundary thing. C to be just to be the skein lasagna module with respect to the empty link boundary. but it may not be a huge issue.
Suppose I take x to be 3 manifold times s1.
Yes.
What do you get then?
That's a very hard question. I hope,
That's not known.
yeah, I hope I can answer that, but right now I think
So it's not known.
it's not known. Unless the 3 manifold is very simple, like a 3-fold or 3-sphere.
Is there any sort of moving structure for your 4 manifolds?
Yes, I will get to that in a bit. A special case of it. So, next I'm going to talk about some easy properties, formal properties of the construction. Well, the very first thing is Wiener expansion is I can recover my input homology. So let me state this as a conversation. Number one, if I take the spin-ascending module of the formal real boundary in L, this is canonically isomorphic to the homology of L. And secondly, so this is a statement on the level of objects, but I can actually make this better to upgrade it to a statement on the morphisms, to get a statement on morphism as well. So let's say we have a link covariance sigma from L0 to L1. Then I get a Green map. More precisely, I can group a corner neighborhood of my 3-sphere boundary together with my covariance inside to the focal with L0. I claim that this defines a map from the skein-ascending module of B4 real L0 to B4 real L1. Well, pictorially, what is this green map doing? So this is my focal. I have some L0 on its boundary. And I'm brewing some I times S3 together with my link covariance inside from L0 to L1. And then, so given any Lasagna filling of the smaller ball B4, just attaching this corner neighborhood onto it gives you a Lasagna filling of the larger ball, a real L1. And you can check easily that all the skein relations that holds in this smaller B4 will also hold in the larger B4, more or less by definition. So you get this green map. But this green map is equal to, agrees with Z of sigma under the identification in number 1. So the skein-ascending module package remembers all about the input homology theory. I'll just say the idea of number one. And I'll skip number two. So I'm going to exhibit to you isomorphism in both directions. So for the backward direction, ZL to the skein lasagna module, I'm going to map some element V to the following class, to a class represented by the following lasagna filament. My input law is going to be a short copy of my tile this? Well, if we have a lasagna filling, sigma we demanded to have skein grade to be homogeneous with skein grading given by the second homogeneous class of the skein sigma. So you have your surface here in your four manifold. Although it's not directly inside the four manifold, it's inside the four manifold with some four balls removed. But four balls are too small in some sense to see anything in the second homology. So actually you can still take the fundamental class of your surface sigma, which will be an element in the relative second homology group. And this element will not depend on the lasagna filling I choose to represent my element. Namely, this is invariant under the skein relations.
Can you explain in both matrix in a little more detail where the things go?
Sorry?
Yeah, in the enclosure map, when you have this UI and J, where do you send it?
To a new label where I use the part of my skein between the smaller balls and the large balls to evaluate.
In the same sphere.
I use this part of the red surface to evaluate the inner label to the outer label. Right, I first cube them up, then I evaluate. But I guess for the discussion of the grading, again, four balls are too small to see second homology class, and you can check that this definition will not depend on will be invariant on the skein relations. And by the way, in a case when X is the four ball, you actually don't get anything new. Everything will concentrate in a single skein grid. I want to say also some words about handle attachments. This is also some form of gluing in these guys. But I guess maybe I need to start with some topological background about how one usually think about four manifolds. Well, at least one way of doing this is by presenting my four manifold by some handle attachments. So just a piece of logical terminology. I will just focus on 40, but we can do this in any dimensions. A four-dimensional K handle positive attaching region is sort of A given by S K minus 1, the K minus 1 sphere, times E4 minus K. So this is a part of, this is exactly this bottom part of my boundary of K. Sorry, BK times E4 minus K. And I guess that as some other piece of terminology, topologists usually call this this central copy of BK the core of my handle, and the dual copy, this is a copy of B4 minus K, the core core. And when we say attach a K handle to some four manifold, we are gluing this bottom part of the foot to the boundary of the other manifold in discussion. So for example, K equals to let's do K equals to 0 first. When K equals to 0, the attaching region is empty. It's S minus 1 times something. S minus 1 is the empty manifold. So attaching the 0 handle is the same as taking disjoint union with a formal. More interesting, K equals to 1. In this case, A is 2 points times B3. And attaching of one handle can be drawn pictorially as what you might imagine. This is exactly what humans would call handles. So this in this picture, this plane is my boundary, is the boundary of my four manifold X. Everything below is X. And the attaching region of the handle is given by two three balls inside the boundary. And the one handle just goes above the picture. So this is the line. And attaching a one handle means adding this yellow part to my manifold X. Maybe let's jump to, well, maybe for the purpose of next talk, I also want to discuss attaching two handles. Attaching two handles, the attaching region is S1 times B2, and the solid torus. And attaching a two handle can be drawn pictorially as follows. So I need to keep track of this attaching region, and really only need to keep track of its core, namely this S1. Its core is going to be some link. Maybe let me just make my picture simple by saying that this core S1 times 0 looks like that on the boundary. Then a two handle is something that looks like this disc, but with everything thickened a little bit. We'll make this picture slightly fatter. This is the picture for attaching a two handle. a solid torus inside boundary X with parameterization of that solid torus with S1 times B2. The solid torus determines the log, the parameterization determines the firm.
Okay.
And vice versa. K equals to 3 picture is not easy to draw, so I will skip that. K equals to 4. The attaching region is just a 3 sphere. And attaching a 4 handle is the same as capping off a sphere component. Of my manifold, capping off the sphere component by a 4. And regarding handle attachments, like, what I can state is the following proposition. So first, full handle attachment is not going to change my skein lasagna model in the sense that X prime is obtained from X by attaching a full handle. Then I get an induced map from the skein lasagna module of X to the skein lasagna module of X prime. By the way, just for simplicity, I'm going to drop the boundary link from now on. You can keep the boundary link while paying some attention to the statements I make, but just for simplicity, I'm going to drop it. Then you get an induced map, which is an isomorphism. So the induced maps comes from just including the Lasagna building in X to X prime. In fact, whenever you have an embedding between two full manifolds, you get such an induced map. So the content is to say this is an isomorphism. And the second, if X prime is obtained from X by attaching a 3 handle, then as we explained, it's also get an induced map, but this time the claim is that it induces a search action of skein lasagna modules. So attaching a 3 handle is killing some part of the skein lasagna module. Those two facts are fairly easy, so maybe I'll again sketch the proof of number 1. Well, basically, this is a general position argument. Maybe, let's see. So this is the 4 handle I'm attaching. This was a boundary S3, and my 4 handle caps this off. The outside of my 4 handle is X, and the whole thing is X prime. How to prove is this induced map is a search action. I need to show every Lasagna filling in X prime comes from a Lasagna filling in X. But so let's say this is my Lasagna filling. Then the skein outside some number of input ports. So in this picture, it doesn't immediately come from a Lasagna filling in X because it intersects this 4 handle. But you can always push this surface off the 4 handle by, for example, you choose a point inside the 4 handle that fairly similar to proof injectivity. Maybe I'll just say in words that every isotopy of lasagna fillings can be isotopes. Right, so for interactivity, you have to show all the relations that you get in all the relations you get in X also, are also there in X prime. The most interesting relation in this case turns out to be the isotopy relation. But if you look at the trace of your isotopy, this is some three-dimensional thing inside the format. And every three-dimensional thing can be some point inside the forehandle, so you can push all the three-dimensional stuff off the entire forehead. Maybe remark with some more effort. One can write down the kernel of a three-handle attachment value. Again, by some general position argument. And one can also obtain formulas, at least theoretically, for two-handle and one-handle attachments. So I should put a reference here, see Randolescu. Method 22 and Randolescu Walker logic 53 for those more general handle attachment formulas. You might think that then, well, we can calculate everything. Why is this theory still interesting? Well, the caveat is that the two-handle and one-handle attachment formulas usually involve some infinite sum and proportionally some infinite relations. So a priori, you might not be able to calculate them in practice. And indeed, as a format for topologies, I can say that almost all complications of a format comes from two handles. And if you don't understand two-handle attachments that well, you don't quite understand skin lasagna modules, when you attach a 3 handle, you are portioning out your skin lasagna module by something. You can make that kernel more precise, but it's quite painful to write it down here. So for 4 handles, you do nothing. For 3 handles, you quotient out. That means, in fact, all the complications does arise from 1 handles and 2 handles. My last piece of properties is about connected sums. So let me write this as another proposition. So one way to create new manifolds out of the old ones is to take connected sums. And it turns out skin lasagna modules behaves quite in a quite boring way with respect to connected sums. Namely, if you take the connected sum of 2 manifolds, skin lasagna module of that breaks into the tensor product of the skin lasagna modules of the vectors. Well, this may be good or may be bad depending on your taste. For example, in cyber-written theory, you certainly don't have such formulas. Maybe I'll do a proof sketch also. So again, I'm going to give you maps in both directions. So in the backward direction, suppose I have lasagna filling sigma I vi for xi. Then I need to give you, I need to tell you where I send the tensor of those 2 elements to on the left hand side. Then, well, what is the connected sum? Connected sum, so in picture is, well, so this is in formula, you delete the 4 ball outside x1, and you delete the 4 ball outside x2, and you glue them along the common free-sphere boundary. In picture, have some x1 here, some x2 here, connected up by some free sphere. Well, if I have any lasagna fillings for x1, x2, I can, as we sketched previously, I can, without loss of generality, assume that the V's, the 2 B4s that I used to perform my connected sum. And then that means those lasagna fillings will actually live inside the connected sum x1 and x2. Then I decide to send sigma 1 v1 tensor sigma 2 v2 to this disjoint union sigma 1 sigma 2 v1 tensor v2. So this is the map in the backward direction. The map in the forward direction is slightly more interesting because a priori, a given lasagna filling may indeed intersect the middle free sphere. entry in a link. It's without loss of generality. Well, let's say input balls are away from this middle grid sphere, and the skein intersect the middle grid sphere transversely in some link L prime. So since the intersection is transverse, in a neighborhood of this S3, the skein will look like an interval times my link L prime. So I can actually perform the following skein relation. I'm going to locate a 3-ball inside this B3 that contains my link L prime. And then I'm going to delete a 4-ball right here. Now, this is just my enclosement relation. I eat up a piece of my skin. Now here, the new boundary link becomes some L prime disjoint union of L prime mirror image. But this input link is a split link. So if you remember, our monoidality condition tells you that if you have a split link, the link homology is going to be a tensor product of the factors. So that means in a skein lasagna module, I can actually break this into linear combination of terms where the labels are some V1 tensor V2 here respectively there. But then using another enclosement relation backward, I can divide this middle 4-ball into 2 smaller balls. Some coefficients here. You get a sum of terms like this, where in this last term, finally, you clear up everything away from the middle grid sphere. I don't know, so here, maybe write this more carefully, maybe lambda I, we label here, V1, I, V2, I. So I declare that my forward map is going to map that element to the sum of lambda I, sigma 1 I, sigma 2 I.
But it's sum over all possible links, right, in S3.
Sorry?
The sum is over all possible links in S3.
No, so.
I mean, if you fix a scheme, then yes, you get one link.
yeah.
But you have to sum over all schemes. Because you can't control what's passing through, right?
So I'm giving a map from in the forward direction. Just need to say where I send each lasagna field into. So the core idea in this forward this proposition is that you can perform a so-called net cutting in the middle.
Sorry, what are lambdas?
Lambda are some coefficients. So here, I'm using the fact that this particular lasagna filling can be, the labels here can be rewritten as a linear combinations of some V1 as a V2 here.
Sure.
And then breaking this lasagna filling into linear combinations of that form. But for the linear combination where I have pure V1 tensor V2, I can further break my B4 into two B4s.
No, I'm not understanding. You assume that the homology of L1 union L2 is just a tensor product, right? We're supposed to know that.
Yeah, this
So why
is
are there coefficients? Who's gonna tell me what the coefficients are?
yeah, I guess you can absorb the coefficient to one of the factors. And this is also true. Yeah, you can do it without coefficients. Yeah, thanks. Yeah, let me see. I have about 10 minutes left. I want to do the trivial example I mentioned near the beginning. Example, Qiuyu Ren homology. So again, recall that Qiuyu Ren homology is this foreign functor from the algorithm's links category, category of vector spaces, sending each link to the one-dimensional vector space and each algorithm to the identity map on this one-dimensional vector space. And I'm glad that you can import this into the skein lasagna module package, so that in the end the resulting invariant for pair X, L is going to recover some second homology. Well, actually, let me just do it without the boundary link. This is going to recover more or less the second homology of your format. Then it's a vector space with one generator for each second homology class. So it's vector space spanned by elements E alpha, one for each alpha in H2. Let me give a sketch proof of that. Maybe before doing that, I think very interestingly, Milan asked earlier about what one gets for three manifolds, and in fact, I think you can extend this further down to two manifolds, one manifold, etc. And if you do all this theory on this trivial example, you can probably recover Maya vectorial sequence, etc. That's a coordinate. But on the level of four manifolds, this recovers the H2. that, I need to tell you where to send lasagna filling to. So in this case, my decoration V is a label in the tensor product of cubes, which is again a canonical cube. So V is a rational number. And I'm just going to send this lasagna filling to V times the generator E second homology class of sigma. This is one generator in my right hand side. This is my assignment. And I claim that this is an isomorphism. So maybe I only have time probably to prove the surjectivity and wave my hand for the injectivity part. But to prove this is surjective, this is actually fairly straightforward. This is because every second homology class in S is represented by a smoothly embedded surface. There are several ways to see this. For example, you can take a line bundle whose first truncat is counter-dual to this class alpha and take a generic section. Then the zero set will be a smooth surface representing alpha. But then once we get this surface, there's a clear candidate of what lasagna filling will be back onto this E alpha. Namely, I can take the lasagna filling given by, whose skein is given by this closed, smoothly embedded surface, and whose lasagna, whose decoration is 1. This proves surjectivity. To prove the injectivity is.
Can I ask a stupid question? Sorry.
Well,
I mean, it's a completely stupid question, but I still don't see, it seems unbelievable, right, that you start with invariance of limits in S3, and you get 4 manifold invariance. Is it obvious that this is like well defined in every 4 manifold, that you really know what it is? And
It is well defined because we haven't made many choices in the definition. It's much harder to say that we understand it in this manifold indefinite. So one can always define 4 manifolds invariant by saying, for example, I take the equivalent class of all embedded surfaces and I mod out some crazy relations, but it's easy to get a well-defined invariant, but it's hard to get a well-defined but meaningful computable invariant. And I guess I want to argue that this invariant is good in the sense that we can actually do some calculation of some 4 manifolds, but not yet on every 4 manifolds. I think that would be too much to ask.
But, I mean, you define it in terms of some words, right? But these, I don't,
has to be